Hello, I'm Brett and welcome back to Math Hacks. Today we are digging into some classic trigonometry. Our goal today is to evaluate sine, cosine, and tangent at specified angles entirely by hand. All of the angles that we'll be working with today will be in radians, and they'll be common angles that you could find on the unit circle, although we won't be using the unit circle or any reference tables to evaluate these functions. Instead, we'll be constructing special right triangles at the specified angle to find the points that we need to evaluate sine, cosine, and tangent. Let's get started. Alright, so just like I said in the introduction, what we are going to be doing today is finding the exact values of trig functions by hand. Now, although we could use a reference table or the unit circle to look up these problems, what we really want to do today is practice constructing the triangles and the points that you would need in order to solve these problems. And yes, we will be finding the exact values and not decimal approximations by doing it this way. So the first problem we're going to look at is just a warm-up problem to get us started. So we are going to evaluate the sine, cosine, and tangent of 0. So the first thing you're going to do in all of these problems today is make a little miniature axis, and this is going to be the same axis that you would have on a unit circle, although we're not going to draw the entire unit circle. We are only going to draw the parts that we need to evaluate our problem. So remember, on the unit circle, we are measuring the rotation around the circle in radians, and we always start on the right hand side here. So this can be thought of as 0 radians, and then as we make a quarter turn we get pi over 2 radians. A full half turn would be pi radians, 3 pi over 2, and of course one full revolution around the axes would get you back to the starting point, which is also 2 pi radians. What you want to remember here is that we're constructing parts of what would be the unit circle. And remember, it's called the unit circle because the radius is 1 unit. So I know that any point that I construct in this little diagram on the right here needs to be 1 unit away from the origin because we are constructing just a miniature part of the unit circle. So to start nice and easy, we're going to find the sine, cosine, and tangent of 0 radians. So that means that I am going to be right here where it says 0. So I'm not revolving at all around these axes. And what I want to do is I want to write a point, and this point is going to be 1 unit over. And whenever you have a revolution that is on one of your 4 axes, it is really straightforward because the distance from the origin is going to be 1. And if it were up, it would be positive 1, left would be negative 1, and down would be negative 1. We are working with a revolution of 0 radians, so it's just going to be this point right here that is 1 over and then 0 up and down. So we are going to evaluate the sine, cosine, and tangent of 0. So now that we have found the revolution of 0 radians, and we have found the point that has a distance of 1 from the origin, we now can use the point to go ahead and evaluate these trig functions. Now the easiest way to do this is to remember that the sine value always corresponds to the y value of your coordinate. The cosine value corresponds to the x value of the coordinate, and tangent is sine over cosine, so that would be y over x. Now that can be a little bit tricky to remember, so what I always remember is that cosine is my x value and sine is my y value, and when you kind of read it together you get cosine. So that's how my silly little way of remembering, because if sine was first and cosine was second, that would say sine cos, which isn't a thing in trigonometry. So cosine, and the x value then corresponds to the cosine value, and the y value corresponds to the sine value. So all I need to do here is look at the y value for sine of 0, and my y value is 0. To evaluate cosine of 0, I'm going to look at the x-coordinate in my point. So the x-coordinate here is positive 1. Now for tangent, we need to remember that tangent is equal to sine over cosine. And if you just kind of remember that when you normally write these out, we write sine, cosine, tangent, then you'll see that it's as easy as taking sine over cosine, so in the exact order that they show up here. So tangent would be 0 over 1 in this case, which equals 0. Or in other words, you can remember that tangent is always the y-coordinate over the x-coordinate. All right, so now let's take a look at a slightly more difficult one that doesn't fall on one of the nice axes here. Let's go ahead and evaluate the cosine of 3 pi over 4. Next, we are going to find the radian measure that we want to evaluate. So in this problem, we want to evaluate 3 pi over 4. And to remember my conversion here, I always remember that if I have a 4 in the denominator, it is a multiple of 45 degrees. So 4 and 45 degrees go together. Now I'm just going to count it off on my coordinate. So starting at 0, we are going to find the revolution around the circle that equals 3 pi over 4, or 3/4 of a pi. So I already know that since this fraction is less than 1 pi, it is going to be somewhere in the upper half of this coordinate axis. So how I'm going to count that off is I'm going to divide this half of my axes into fourths. So 1/4, or pi over 4, would be here at a 45-degree angle. 2/4, or 1/2 pi, would be here at a 90-degree angle. That means that 3/4 pi would be another 45 degrees over. So it's going to land right here. Now that you found the angle that you need to evaluate, the next thing to do is, if that angle isn't on one of the 4 axes, you're going to make a triangle with the horizontal line. So I'm just going to draw a little vertical line here, and that's going to be a right triangle. So this is the triangle I'm going to be working with. Next, I want to find my reference angle, or the little angle inside this triangle right here. Now, we know that if my denominator has a 4, I am working on intervals of 45 degrees. So remember, I went 45 degrees, 90 degrees, 90 plus 45 is 135 degrees, and then another 45 degrees would put me at 180 degrees, or pi radians. So that means that this inside triangle here has a degree measure of 45 degrees for this angle. The next thing I'm going to do is just over on this side, since I have a special right triangle here, which you should always have in these problems, is draw that special right triangle a little bit bigger so we can fill in the proportions. Now, one of the few things that you have to memorize in order to do these trig functions by hand is your 2 special right triangles. So you're going to need to be familiar with your 45, 45, 90 degree right triangle, as well as your 30, 60, 90 degree right triangle. So recalling from geometry, a 45, 45, 90 degree right triangle has side proportions of 1 and 1 on its 2 legs, and square root 2 on the hypotenuse. Now, notice one thing here. I said that because the triangles and the points that we are drawing in this, what would be a unit circle if we filled it all the way out, has a radius of 1. So that means that the hypotenuse of my triangle here needs to have 1 unit. And notice how our special right triangle, the proportions that we're given, it doesn't have a hypotenuse of 1 unit. it has a hypotenuse of square root 2. So what we're going to do here is we are going to adjust this triangle so that it fits correctly in our unit circle. To do that, all you need to do is divide the hypotenuse by itself so that it equals 1. So I'm going to divide square root 2 by square root 2. And to keep the triangle in proportion, I am just going to divide both the legs by square root 2 as well. So once I do that, I get my hypotenuse of 1, since square root 2 divided by square root 2 is 1. And then I get legs of 1 over square root 2. So what I need to do here is rationalize the denominator. So I'm going to multiply both of these by square root 2 over square root 2 on both of these side lengths so that I get the denominator rationalized. Now this is kind of tiny here, but what I get is square root 2 over 2 for both of the legs. And don't worry if this seems like a lot of work right now. As you work with these problems, you're going to be working with a lot of 45, 45, 90-degree triangles. And once you do it a few times, you'll start to remember that the side lengths of the 45, 45, 90 triangle, when adjusted, are square root 2 over 2 and 1. So the next thing to do in our problem is to go back over here to our drawing and fill in these missing side lengths. So I know that both of the legs in this are going to be square root 2 over 2. Now because this triangle is sitting on a coordinate axis, I need to make sure that whenever I go left or down, I have a negative value because those are negative directions on my axes. So this side length here, because it's going left, is going to be a negative square root 2 over 2. This side length, because it's going to go up, is going to remain a positive square root 2 over 2. Now what we're looking for in this, if you've forgotten, is that we are looking for the point right here. And that point would be the point on the unit circle if I were to draw this entire unit circle out. And now we know the value of that point because we know the x distance and the y distance. So I am running out of room here, so I'm just going to draw a little arrow. So this point right here is at the coordinate negative square root 2 over 2 and a y value of positive square root 2 over 2. Now we can do the final step, which is to evaluate the cosine of 3 pi over 4. And remember, cosine is our x value. So all I need to do here is look at the x value of the coordinate at 3 pi over 4. And that value is negative square root 2 over 2. We'll start with our coordinate axes. Next, we need to find the angle of 7 pi over 6. So, looking at this fraction, I have 7/6 pi. Now, 7/6 is larger than 1, so I know that it is larger than half a revolution, since pi is half a revolution. So it is going to be in the bottom half of my coordinate axes. Now just how far past pi is what we need to figure out. So I know I have 7 pi over 6, or I can think of that as 7/6 pi. 7/6 is the same as 1 and 1/6. So it is 1/6 past pi, so just a little bit past it. So this revolution would start here and it would go just a bit past. Besides pi over 4s, the other value you're going to run into on the unit circle is pi over 6s and pi over 3s, or some multiples of those. Now what I always remember here is that pi over 6 is equal to 30 degrees, and pi over 3 is equal to 60 degrees. So see how the 6s and 3s are mismatched together. If I have a 6 in the denominator, it's going to be 30 degrees, or a multiple of 30 degrees. If I have a 3 in the denominator, it's going to be 60 degrees, or a multiple of 60 degrees. And remember, like in the last one, if I have a 4 in the denominator, it'll be a multiple of 45 degrees. So that's my quick little memory aid to help guide me, because the next thing we're going to do is, of course, connect the line to our point with the x-axis and make a right triangle. Now, I should mention here that there is one other thing that sometimes students mess up when they're first learning how to do these, and that's they make the mistake when they're drawing their triangles. So, say our triangles here. They make the mistake of accidentally connecting it to the y-axis. Now, the quick way to remember which axis to connect these to is that you're always connecting them to the x-axis. So in some way, your triangles are going to be in one of these 4 orientations and not in one of these orientations. And how I keep straight which is the correct orientation for your triangles is that the correct one looks like a bow tie being worn the correct way, right? We would wear a bow tie horizontally. If your bow tie was going up vertically on your neck, it would be silly looking. It would be wrong. So the correct orientation of your triangles needs to fit in a bow tie. So one of these 4 triangles, not this triangle. The next thing we need to do is find the reference angle, so the angle inside of this triangle. And what that's going to do, of course, is it's going to tell us what our triangle's proportions are. If you're looking up angles that are on the unit circle, which are typically how these problems go, then you are always going to have special right triangles, or you're going to have a point exactly on the axes. Remember, this is 7 pi over 6. And I said over here that I was going to go 1/6 past pi, or 1 pi. So that means that this little angle over here is pi over 6. And remember, pi over 6 corresponds to 30 degrees. So what I have is 30 degrees inside here. I'm going to go ahead and draw this special right triangle a little bit bigger on the side so we can work with it. If this angle is 30 degrees and this angle is 90 degrees, that means that the remaining angle here is going to be 60 degrees. Now, pulling back from our memory of geometry, we need to fill in the side lengths of the 30, 60, 90 special right triangle. And the proportions for that type of triangle is 1 square root 3, 2. So 1 always goes across from the smallest angle. So here's my smallest angle. It corresponds to the smaller leg, and that is going to be the smallest number in those proportions, which is 1. The hypotenuse is always the longest leg in any triangle, so it is going to be the largest number in my 3 values for this proportion, which is 2. And the leg across from the 60-degree angle is the middle value, which is square root of 3. If you forget that the square root of 3 is smaller than 2, what you can remember is that 2 is the same as square root 4. Then when you compare square root 4 with square root 3, you see that square root 3 is smaller. All right, just like in our last triangle up here, we want our hypotenuse or our radius on this circle to always be 1. So I need to divide all of the values in this proportion by 2. Why did I divide those by 2? Remember, it's because I divide by the hypotenuse so that the hypotenuse equals 1. So 2 divided by 2 equals 1. My other side lengths are going to be 1/2 and square root 3 over 2. Again, you'll be working with a lot of 30, 60, 90-degree triangles when you're constructing the unit circle and evaluating trig functions from the unit circle. So these numbers will become very familiar to you. Once again, if I am going left or down on my unit circle, I need to make sure that I correct these values to be negative values. So here from the origin, I am going left square root 3 over 2. So I am going to write a negative square root 3 over 2 here. I am also going to be going down 1/2. So I need to make this a negative 1/2. So that means that the coordinate of this point, which would be the point on the unit circle, if I were to draw the entire unit circle out, is negative square root 3 over 2 to the left and down 1/2. And finally, we can actually answer our question now. So our question is, what is the sine of 7 pi over 6? So I have found the angle of 7 pi over 6. I have built my special right triangle, making sure the hypotenuse is equal to 1. I have made the coordinate point, and now all I have to do is read off the y coordinate for sine, because remember, cos, sine. So sine is going to be negative 1/2 here. Another thing you might run into in these problems are negative angles, so negative radians. And what they represent is the revolution in the opposite direction. So let's go ahead and draw our axes. Normally, we travel counterclockwise when we're applying our radian measures. If I have a negative radian value, that means I'll be going in the opposite direction. So I'm going to be going clockwise around the unit circle. So negative pi over 2 means I am going, instead of going to pi over 2 forward, I'm going that same distance but in the opposite direction. So that means I'm going to be going backwards pi over 2 or 90 degrees. So the point for this one is going to be 1 unit away from the origin here at 3 pi over 2, because this is the same as negative pi over 2. So a rotation of back 1/2 pi on the unit circle is the same as going forward 3 pi over 2. This is the same point. So that means my solution for this is going to be exactly the same as if I were evaluating the tangent of 3 pi over 2. This one is a nice straightforward one because our point falls on one of the 4 axes. And when it does that, we don't need to draw a triangle. We simply know that this is going to be 1 unit away from the origin. Because I'm going down, this is going to be a negative 1 on the y value. So this point right here is simply 0, negative 1. So I've gone 0 on the x-axis and simply down 1 on the y-axis. Now, the next thing to remember is that tangent is sine over cosine, or the y value over the x value. So when I go ahead and take the y value at negative pi over 2 and divide it by the x value at negative pi over 2, I get negative 1 divided by 0. Now, of course, I can't divide by 0. So in this situation, you are going to say that the solution to this is undefined. And this will make sense when you go ahead and look at the tangent graph, because at negative pi over 2, there is a vertical asymptote. And that vertical asymptote is there because our function is undefined at that point. All right, so the last type of problem I want to look at today is evaluating a trig function when the angle is greater than 2 pi. So we are going to evaluate the tangent of 11 pi over 3. So the first thing we need to find on our axes here is we need to locate 11 pi over 3. So let's take a look at 11 pi over 3. 11 pi over 3 is the same as 11 thirds pi. Now 11 thirds, let's change that into a mixed number real quick. So 3 goes into 11 3 times, since 3 times 3 is 9, and I'll be left with 2 thirds over. So this is the same as 3 and 2 thirds pi. Now sometimes thinking about this as a mixed number just makes it a lot easier to visualize, because what I see here is I need to go 3 pi units and 2 thirds pi units. Another way to write this is simply 3 pi plus 2 thirds pi. And that's a really handy way to look at this problem. So let's start by revolving 3 pi units around our axes. So I start here at 0. I go halfway around, that gets me 1 pi. I go another halfway around, I get to 2 pi. Now the way this works is we can just keep doing that and counting up. So if I'm at 2 pi here, another half revolution will get me to 3 pi this time. So 3 pi and pi are the same. Now that I have 3 pi, I want to add 2 thirds pi to that. So remember, a half revolution is pi, so I want to go 2 thirds of the way to the next revolution. So if I kind of think of, there's 1 third and 2 thirds is going to be here. So just as a little recap there, what we did is we went all the way around once to get 2 pi. Then we went halfway around to get to 3 pi. And then we went 2 thirds to get another 2 thirds pi, which would bring us to 3 and 2 thirds pi, or 11 thirds pi. Now that we found this point, we're going to construct our triangle. And we need to find the reference angle. So we are really curious as to what the little angle in this triangle right here is. So we remember that the last thing we did here is we went 2 thirds of the way over. So that means the distance between here and here is 1/3 pi revolution. So pi over 3. And if you remember from our memory aid, pi over 3 corresponds to 60 degrees. And pi over 6 corresponds to 30 degrees. So this pi over 3 here is the same as 60 degrees. I'm going to draw this triangle a little bit bigger on the side here so we have a better look at it. Next, I want to fill in my proportions for my 30, 60, 90 special right triangle. So across from the smallest angle, I put 1. Across from the largest angle, I put 2. And the in-between leg is square root 3. Next, to make sure that my distance from the origin out to this point is 1, I divide everything by the value of the hypotenuse. So in this case, dividing by 2. So that 2 divided by 2 equals 1. And I have 1/2 on the short leg now and square root 3 over 2 on the longer leg. Next, I'm just going to fill those in on the coordinate axis. And I'm going to make sure that if I go left or down, I add a negative. So in this case, the leg length here is a negative square root 3 over 2. Now I can go ahead and record the point. So this point right here, to get to this place, I need to go right 1/2 and down square root 3 over 2. All right, we're almost there. The last thing we need to do is evaluate tangent at this angle. So tangent is sine over cosine. So I need to find sine of 11 pi over 3 and cosine of 11 pi over 3 and divide those. Our little memory trick here again, of course, is the coordinate points correspond to cosine. So cosine is the x value, and sine is the y value. So I'm simply going to place negative square root 3 over 2 in the numerator for sine, and 1/2 into the denominator for cosine. Okay, so a little bit of arithmetic here. We have a fraction divided by a fraction. So we need to flip and multiply. So I'm going to take the reciprocal of the denominator and multiply it with the numerator. I almost wrote that wrong. So this is going to be flipped upside down. So I'm going to be multiplying by 2 over 1, and I'm writing in pen, so I don't have an eraser. So just bear with me here. Next, what I see is that I can nicely cross-cancel these 2's, and I'm left with negative square root 3 over 1, or simply negative square root 3. All right, so that is the answer to tangent at 11 pi over 3. Thank you so much for joining me on another episode of Math Hacks. Remember to click that subscribe button before you go so that you can get all the math help you want when you need it. Till next time, I'm Brett, and thank you so much for joining me.